So I just heard that in the LinkedIn post it was saying that I was talking about casual models instead of the causal models. So for those that want a casual model, I don't have those, but I hope the talk will be casual enough to follow for you. Okay, yeah, so as I said, I hope to inspire you a little bit in your own project to think about the causal and the predictive components of the problem that you're facing. And I'll do so by using an example of irrigation in a greenhouse and how we apply this at source. So this is the outline. I would like to start with a short scenario to get you into the causal thinking mood. Then I'll tell you about the problem. We're applying this to irrigation in greenhouses. Then I'll go a little bit more into depth in how we approach this. And then I hope to give you some general advice on how you can apply this in your own projects. So first, the short story. This is a scenario, and I think I can be honest with you, I'm a little bit cheap here. I used exactly the same story that I used last year during the PyData conference, but I just really felt it helps you to get into the mindset of thinking about causality. So bear with me, here comes the story. So there's a freshly hired data scientist and a manager, and the data scientist fresh on the job asking, okay, what shall I start doing? And the manager is saying, what about making a model for predictions, for sales? I'm sure that will be something super useful. And the data scientist asks, okay, but how is it exactly going to generate business value? At which the manager replies, well, we can think about it later. Let's not worry. I'm sure it will be super valuable. So the data scientist goes to work, and 2 months later, she has this amazing model with a super small prediction error. And at that point, the manager says, this is awesome. Now let's predict what happens when we change the price to decide whether we give a discount or not. And if you ever feel you're in such a scenario, you should raise a red flag. Because what's happening here, you start off with a purely predictive problem. And then it turns out it wasn't such a purely predictive problem to start with. Actually, it's more of a causal problem that you're looking into. So, and why is that the case? Here's the formula of what means it. What does it mean when you have a causal problem? It's when the probability of outcome y given observed x is actually something different than the outcome of y when you start influencing x, so these features. And this is something different, and this is really at the core why you might have a problem if you start with a predictive model and you end up answering causal questions in the end. So I hope you're all in the causality mindset now. Let's go to our topic, irrigation in greenhouses. But first, why do we have greenhouses in the first place? Nowadays, still 2 billion people around the globe suffer from malnutrition, and we have a growing population. So with the limited space we have on our planet, the only way how we can feed the world with a healthy diet is in some sort of controlled environment agriculture, of which greenhouses is one option. So why does this work well? It's climate resilient, it allows for local production, but moreover it gives up to 50 times as much yield per square meter. Moreover, so, and we'll be talking a little bit more about this topic, is the water can be recycled inside the greenhouse, which makes it much less water that you need to use. Also, the fertilizers can also be recycled, which is a very good thing because you prevent any pollution by runoff into the environment of these fertilizers. So why don't we see much more greenhouses around the globe? It's because there's a complication. It's if you have such a highly advanced greenhouse, you actually still need growers that can successfully operate these greenhouses. And they need to have a lot of experience. Think about at least 10 years before you can do this. Moreover, even with an experienced grower, it might take several years before you can make a new greenhouse profitable. So what happens, especially abroad, where they do not have such expert growers as in the Netherlands, they invest a lot of money to make a sustainable greenhouse, and they go bankrupt within a year because they do not have the expert growers to make it profitable. And that's where we, with Source, come into play. So we help growers to solve these challenges using machine learning products. So Source was founded 2 years ago, and we're currently with 60 people dedicated to helping growers to make it much more easy to scale greenhouse growing across the globe. So onto the topic of irrigation. Unfortunately, I can't explain all the things that we help growers with, but irrigation is the topic for today's talk. So how does irrigation work in greenhouses? In these high-tech greenhouses, typically the plants are not inside the normal soil, but they are grown in these kind of slabs. And these slabs actually make it possible to capture any water that comes out of it and do this recycling of the water and the nutrients. So that's why they're in slabs. So how does irrigation work? You see these small white tubes and black pins, and those are used by computer-driven precision irrigation inside these slabs. The slabs gets wet and starts filling up with water, which is called saturation. And when it's fully saturated, the water comes out in the bucket you see below in drain. And the water can be recycled. And in the middle, you also see a measurement device for how much drain is actually coming out of the slab. So what do the roots look like? So here's a picture of healthy roots. You can see there's a lot of roots, and they are nicely wide. So if you think about the water inside this slab, of course, when it's a lot of sun, you want to have a lot of water for the plant to have optimal production. However, you cannot have completely wet slabs all the time because it's not healthy for your roots. The roots need to have oxygen to be healthy. If you just completely have a wet slab for a couple of days, these turn brown, they start to rot, and your plant dies. So we want to have a lot of water during the day, but then also have little water and oxygen inside the roots to have healthy plants. So it's important that we measure the amount of water that's inside the slab. So there's two sensor types that are mainly used to do this. One is using scales, mostly used in tomatoes. The tomatoes hang from a wire, and then I put a scale underneath the slabs, so you can actually measure how much water is inside. The nice property of this setup is that you know 1 liter in is 1 kilogram on the scales. So actually there's a physical relationship that tells us, okay, what is the effect of irrigation? However, if you grow other crops like peppers, they stand on top of your slab. So it doesn't work because you also get the weight of the plant. In that case, we use these in-slab sensors. It's pins going inside the slab, and they can measure water content. But in this instance, it's not really clear what the effect of irrigation is on the water percentage inside this slab. So that's where we would need to have something causal. So, a summary, how does this work? You have the slabs, water gets in during the irrigation shots, and the water gets out in two ways. Either the plant takes the water, or if the slab is fully saturated, it comes out as drain. So let's look at some data on what this looks like. So you can see during the night, the slab is quite dry. So we have percentage water inside the slab. Is it fully saturated or not? It's quite dry. And then in the morning, you start giving several shots, and you make sure that when the sun is shining a lot, then you're at maximum saturation. So there's a lot of water for the plant, so it can grow optimally. And then at some point in time, you need to stop. And this is quite hard to decide when you exactly need to stop, because you need to make sure that you get dry enough during the day to maintain healthy roots. But when you need to stop depends on how much water the plant will be going to take. And that depends on a lot of factors. So this is a very hard task for growers. Every day think about, okay, when should we stop irrigating? And that's what you want to help them with. And you can already hear that this problem has kind of two components. One thing, we need to go up with our shots, so we need to have the causal effect of a shot. But then also, we need to know when we stop irrigating, and that's much more of a predictive task, because we need to predict how much water the plant is going to take. So there's really two components to it, one more causal and one more predictive. So, onto our approach. How do we approach this problem? Let's start with a black box approach. And with black box, I mean, just take any features that have predictive power and throw them into the model. Because if you look at this data, we actually just have a time series. Oh, we have time series methods. We get a bunch of data, and then we can make nice predictions. How hard can it be? So what kind of features have predictive value? It's outside weather. Most importantly, radiation that's outside. But it's more complicated than that, because in the greenhouse, there's a lot of controls. You can open the windows, you can turn on the heating, you have screens, so there's a lot of things that influence the actual climate inside the greenhouse. Then there's lags. I'll come back to lags. Lags can be very powerful for prediction, but quite dangerous if you want to do causal effect estimation. And then last but not least, we have irrigation and drain. The intervention, the treatment that we're interested in. So let's just throw all of them into a model. So which modeling method do we like to use? I'm going to show results for gradient boosting, light GBM, and a linear regression, and I would like you to choose either of those Which one do you think is better at estimating a causal effect? So if you can put your hands. Anyone like GBM? Anyone? Yeah, a couple. So linear regression, you have to choose, so that's everyone else? Okay, that's more. Yeah. Okay, so first explain the graph. So on the x-axis we have the irrigation in liters. On the y-axis we have the change in saturation inside your slab in percentages. So, and for this example, I want to show you a ground truth. So we actually take the scales here. And there we know 1 liter in is 1 kilogram on the scale. So we can actually calculate what's the ground truth here. That's the blue line. And this is what we're going to use to show you how these modeling methods work. So this is the light GBM. And actually, I was really surprised because this doesn't look that bad. So we kind of got lucky. Even in the beginning, it seems quite near to the ground truth and then a little bit less. So yeah, we got lucky here, just throwing some features and does quite well. Surprisingly, if you take the linear regression, it's worse. So that's really giving you an idea like, okay, maybe it's not really about the specific modeling method that you use, but maybe it's all about the features that you select. So a little bit of a side step here. I want to go into double machine learning, another method that's specifically focused on using machine learning to estimate causal effects. So we do the same thing, we throw the features in, but I'll take a side step in explaining you a little bit about how it works. So I use the ecom-ml package, I encourage you to try it, and I'll use these formulas to explain what it does. So here again we have the outcome y, and we have the treatment t, and what we're interested in is the effect theta in here, which can depend on x, which are some features. You have x and w together is anything that could help you resolve these causality problems, confounding errors. It might actually be a common cause or something that's indicating a common cause. And in the black box approach, we just throw anything in. So what's the idea? We actually do a regression using the residuals of the outcome y and the residuals of the treatment t. And these residuals are calculated like this. So we use these formulas, g x of y and f x of y, that we use to calculate these residuals. And the beauty of it, we can pick any machine learning model to fit g and f, and we can still get results, good causal estimations. So there's a bit of code. How does it work? You can use the ecom-ml package. In this case, we just take a linear model for theta, for the effect, and then from scikit-learn, you can take random forest regressor or whatever you want to fit it. You get your point estimates and you can get confidence interval. So please try it home. For now, we do exactly the same black box approach. Select all the features, just throw it in. And as you can already expect, well, purple line here, it looks better than linear regression, but it really doesn't look that much better than just throwing it into a light GBM model. So you'll know maybe it's not that much about the method, it's all about the features that you select for your model. So we need to be smart about it. So how do we approach this? We have this line, and if you look at it, you see when the line goes up, we have irrigation and rain. But there are a lot of data points inside this graph. There's no irrigation and rain. So we know we only have the water uptake. And this is an opportunity. So what is our approach? We first train a predictive model of the water uptake with any data point that doesn't have irrigation and rain inside. Then we use those predictions to subtract the predicted water uptake from those other data points, and then we can estimate our causal effect of irrigation using a simple model. And if needed, you can iterate a little bit between fitting these models. And this is the result. Orange line, and you can see, maybe not exactly ground truth, but clearly much closer. So it really helps to think about what features do you select, and do you have opportunities to fit this model in a way where you have a predictive component and a causal component. So going back to the remark before, with the light GBM we got lucky. But we don't really want to be lucky, right? We don't want to be something random. Maybe we get a causal effect, maybe not. So why does this happen in the first place? As I said, lags are quite dangerous. For prediction, they are quite powerful. And why is that? If you look at what happened yesterday in the saturation and what the water uptake of the plant was yesterday, it has the opportunity of capturing a lot of things that you cannot really measure in a greenhouse. It's just like the whole system behaves a little bit like yesterday. So that's good. However, for causal inference is dangerous, especially if we start automatically retraining these models. So imagine if a grower changes the climate computer, so how it exactly works. So okay, now I do a specific moment in time, so I do this irrigation shot. If that happens, then suddenly the model will see that right exactly inside the leg of yesterday, the saturation goes up. And the model cannot distinguish anymore. Is this because of what happened yesterday, or is this because we irrigate now? So this is a risk if you use less, especially it might look good when you start with, and then you retrain your model, and suddenly your causal effect it just goes to shit. And another one that's very important is be careful with features that might be caused by the treatment. So let's say you do some random feature engineering and you say, okay, at each shot, the start time of each shot, I make a feature because maybe it's something I need to control for in my model. And you put it to the model, you go wrong because the model again can distinguish between is it the irrigation or is it the start time that's causing this. And if you think about it, if you engineer it like that, actually it's a cause of the treatment rather than something that would be a common cause of treatment and outcome. And another example, of course, drain. Drain happens because we irrigate, so be careful with selecting it into your model. So that was our application, and now I hope to share a little bit some advice and thoughts on how you can maybe think about these causal and predictive components in your own project. So let's say we have the scenario. We start off with a prediction problem. How can you identify that it might be that you have some causal components to your problem? So one of it is good to think about this. So the predicted outcome of Y, is it actually something we try to influence by changing something in the features? If so, what are those features? Because you need to have a causal approach for them. Then generally just look to the features, and is it stuff that's influenced by humans, then probably you should think about is it the causal component. Also, if you're doing scenario comparison, it could also be an indicator that you need to have a causal approach. And it doesn't even have to be exactly that a human is influencing. But for example, if you say outside weather, radiation, it's not something that we change. But if for some reason we really want to know the effect of radiation on what we do, then you have a similar problem that I described before, the legs. So remember, you have radiation, but inside the legs that we use in our model, it's also kind of the effect that the weather might be similar to what it was yesterday. So if you throw it in the model like that, you don't really get a causal effect per se. So not only for things that humans can control. And then lastly, sensitivity analysis. If you find either during development or monitoring that you're doing some kind of sensitivity analysis, says please check that whatever you're checking in your features, you're checking in your sensitivity analysis, whether it actually is something that needs a causal approach. In general sensitivity analysis, besides model monitoring on like prediction performance, it's a really good idea to monitor your sensitivity for any causal components inside your model. Because that's just what you need to check when you retrain. Think about the example where the changes in the climate computer were made. I mean, that's what you want to capture if you retrain your model. Then the other way around, when can we use these predictive components? It's if we just want to do a prediction without directly influencing the outcome. Then we get more free, okay, don't worry too much, we can make a predictive model. An example would be the water uptake. We just need a prediction for the water uptake to define the stopping time. It's not something that we're going to actively influence. So there you can use predictive components. However, also here, don't go blindly selecting features, because if you have this predictive component, you need to be careful for model leakage. And what this means, if you need to stop irrigating and we need to do prediction for during the night, then there's a lot of features inside the data that actually isn't available at the moment of prediction. So you also need to be careful with these components that you actually do not create leaky models. So how can we estimate this model? First check is maybe we do not need to fit a model at all. It was the example of 1 liter in is 1 kilogram on the scales. I mean, just use that, right? Or maybe look into the literature, and maybe it's even better to get something from literature and use that instead of fitting your model. Then the example I gave is there might be an opportunity to do this multi-stage approach. So in our sense, first estimate a predictive model for the water uptake, and second step, estimate the causal model. However, it might be hard to do, and then you might want to consider doing estimation of all these components together. And then you would have to make a custom model in TensorFlow, PyTorch, or one of my favorites, PyMC3, if you want to have a Bayesian approach. So that's also an option. So in my example, I could show you how well we did because I actually knew the ground truth. But in many cases, you do not know the ground truth. I mean, it's the whole point why you're looking into modeling this stuff, right? So for testing, one of the methods that you can try if you want to test your method is get the effect out, then put an effect in with a specific size. And then you can test your method and see whether it actually can retrieve the correct effect. I mean, it's not 100% foolproof, but it does give a way to give you some handles on, okay, is my method actually working? Do I get the causal effect that I actually put inside of my data? So, last advice I want to give, I hope this is the takeaway. Just never blindly select features for your model. Really spend time thinking about them, okay, what do they mean, which one should actually do or not. And then second, worry about the modeling framework. So that's it. Any questions?
Oh, you managed well within the time.
Yeah.
So does anyone have any
quicker than I
questions
thought.
for Ruben? Because then we're going to throw the microphone at you. Ooh. Ooh. Oh, nice.
That's a good catch. I have a question that's actually related to the last slide that you just showed, where you explained different methods that you can use to deal with causality in general. And what about just a control group?
Yeah, so okay, so that's I decided not to put it in. But if you can A/B test, please A/B test. But in many cases, you can't A/B test. Like
Yeah, exactly. Because in our case, for example, we can't really do that. So then it's like.
Yeah, so then you. But it's always good to think about, okay, what would an A/B test look like? With us, it would be like having a lot of greenhouses and just like have a random sample, right? But that, I mean, that's just too costly because you just probably are going to lose a lot of crops. So that's yeah, so that's, but if you can A/B test, you should do it, but keep in mind the cost. So to give a bit more background, we do have research in this area, right? So it's just going from Wageningen University. So you do have these controlled experiments where they do this, but then often you can't really get to this level of detail as we do here, right? It might be, okay, if you do not give any water or substantially less water, do we see in our test any effect on the plants? But that's, I mean, good for research, but it doesn't really help with solving these practical problems because you need to be much more precise on how you should steer it. And then it's just too costly to do an experiment for everything.
Yeah.
Good question. Anywhere there in the middle. Yeah, get ready to catch. Oh,
this is going so smooth.
Hi. Wouldn't the...
if you keep the thing, like you have to talk into the star thingy. You don't have to keep it that close, but then we can hear you.
I hear my voice. Wouldn't be also this problem the domain of Kalman filters?
Sorry?
Like to optimally control basically irrigation, where we have the dynamic system that switches between what should be during the day and what, well, optimally should be during the night. Like from a mechanical engineering point of view, usually like people approach this also as with Kalman filters. Is it something that we could also implement here?
With Kalman filters. Yeah. So Kalman filters goes in any category of like time series. Like you could do LSTM, like whatever, right? You can do that for the predictive part, but be really careful with the causal part because the exact example of a lag of 24 hours. I mean, that's just like super many more lags inside your model if you start using these kind of models. So it becomes really hard to kind of disentangle what's the causal effect. So that's one, and the other one is if you need to predict a long time ahead, then you need to think about error propagation inside such models. Yeah, but sure, for the predictive component, I mean, pick anything that works. But for the causal components, it would be tricky.
Okay, thanks.
Yeah, I have a question about this prediction. So the grower has in mind what he wants to do for the future things. So what is the predictive part of your model? Where do you use it for?
To decide the stopping time. So it's like the target is, okay, we need to reach this dry down. right? But then the question is, when do you stop? So we use the predictive model to predict the water uptake, and then you calculate back, and then you know when to stop. So that's simple, I think.
So the idea is that it's then also acting as a help or replacement for an expert, that you don't necessarily need an expert grower to tell you you have to stop now, you can use the model.
Yeah, so that's the really hard part. You really need to imagine the grower every day has to check, how's the weather and what will it do, and should I start earlier or later? And that's, yeah, I mean, that's just hard. You need a lot of experience, and it just takes a lot of work. So that's where we try to help them with.
Yeah. Over there?
Hi.
You have an easy throw and then you miss.
Thanks for the talk. It was very interesting. I was wondering, do you model per plant or per plant type, and how much variability is there? Like, do you need to keep learning, or do you learn a model once? And
okay, that's a very good question. For the other modeling we do, it's like how the plant develops. The type of plant really makes a lot of difference, even between species. So that's like a large part of the job. For these models, they train quite fast because we get quite a lot of data. So it's like really quickly, and then, okay, just look at the plant behavior now. And then it's a little bit less depending on what plant you have. Because I mean, how the plant behaves is, of course, depending on a lot more things than the species of the plant. But in any case, I mean, we just have the opportunity that we can learn this pretty fast. So that includes like the specific species of plant.
Thank you.
Do we have any more takers for the cube? All the way in the back. You think you can?
Oh, but first,
yeah,
I have
sure.
someone in front.
Thank you. Very interesting presentation.
Thanks.
I don't want to reiterate the first question too much, but so causal inference is notoriously difficult in some domains, right? Like marketing. Even if you can successfully A/B test, was your marketing campaign so successful, or did the opponent's marketing campaign suck? Right? You don't know. But this strikes me as a domain where you have full control over the feature space, right? So you briefly mentioned you could actually create a physical copy of the greenhouse and just essentially A/B test away, right? And you could actually create a mini version of that. So I don't see why it would be that costly.
Okay, so that's going back to my previous question, right? I mean, is that costly because greenhouses are expensive and you will lose on your harvest, right? I mean, so that's the costly part to it. And especially, I mean, setting up a one-off experiment is not that bad, but it's like continuously knowing, okay, where should we exactly put this? I mean, that's really hard. So to be honest, it's not even that much of a question for us, like prove exactly how much better you did. I mean, that's not what we're talking about. The growers know this is super hard and we just help them with it. And if it helps them to become successful, we don't even claim to the, like with the marketing campaign, say, okay, this is exactly the uplift. We don't even do that. It's just like, we helped you achieve this. Also, maybe give a little bit background of the plants. It's like stability for the plants is really important because the roots develop where the water goes. And this is really where there's also a lot of impact. It's like, okay, for the growers, it's really hard to get the dry down stable because of weather conditions, because of everything. And that's what we help them with. And that's what's really beneficial for the roots.
Thanks.
Another question? I think it was all the way there in the back.
Can you raise your hand, please?
Yes.
Okay.
Are you going to try?
No. I don't want to injure anyone, so. Here you go.
Apologies. Hey, thanks for the talk. Very big respect to anyone who does causal inference in practice. So. A question for you. Since your problem is so practical and I imagine costly, I just wonder, did you have enough observations of the causal variable along the spectrum? Like, the question is motivated with the previous experience of mine that is like sometimes it's very hard because some things don't happen in reality, right? With some combination of features. Yeah,
so you were lucky because especially with the skills it's pretty simple, right? You put water in and then the weight goes up. If you with the inslabs it's a little bit more complicated than that indeed. But still the fact that it's across one feature helps. So you can kind of check if it's inside this range. So there's not, okay, you cannot model without making assumptions, right? And here we make some assumptions that I mean, it's not like super many interactions effects of everything. You could use the double machine learning methods to have even non-parametric. You could do like the causal forest. But to be honest, I mean, the more you allow for these kind of things, the harder indeed it gets. Like, okay, yeah, what does this actually say? And if you start making predictions, do we, in these high dimensionalities, move somewhere out of the area that we ever have seen data before? So in that sense, I mean, it really helps to make assumptions. But if you can make those assumptions, then I mean, then you have an interesting challenge, I suppose. That's what's making the work fun. I mean, it would just be boring if it's just like take your features, fit your model, and that's it, right?
We have time for, yeah, we have a couple of minutes there. Yeah.
Hi, thank you for the talk. I was just wondering if the physics failed with respect to causal inference, or was there any comparison made between physics and causal inference?
Yeah, so the ground truth here was like the physical equation. Yeah, okay. So I think what you're saying that physics might also not be perfect, right? To some extent that's true, because I mean sensors, I mean no sensors are perfect. So in reality it might deviate a little bit from the ground truth that I put here. But yeah, still with these skills, it's quite close, right? 1 liter in is 1 kilogram, so we can pretty well calculate what is happening with the sensors if you irrigate.
So it is possible to do like a predictive model plus physics-based model?
Yeah, so that's, yeah, exactly. So if we would have the skills, then we could use the physics model to do the irrigation, and then that could be the first step. And then we take the irrigation out, the effect of the irrigation, and then we can train our predictive water uptake model. So that's, yeah, that would be a perfect strategy, yes.
Okay, yeah, thank you.
I think that's it for time, or do you want to do one more?
We can have one more question.
We can do one more question.
Yeah.
Yeah.
The questions are amazing, so please, another one.
Oh, perfect.
Wow.
No practice, just so you know.
So, do you hear me? Okay. I mean, from a person coming from systems and control background, I very much enjoyed the solution, because in that community, they basically try to use dynamical models like based on physics, differential equation, and also Kalman filter is also based on that. And one of the drawbacks there is that because basically they can't always find differential equation for models, and that's where they would use data-driven methods like machine learning and these methods. So I was wondering if you were also able to compare the solution that you had with any sort of solution coming from more like systems and control perspective. Was this, let's say, problem also already addressed via different solution? I mean, causal inference, because you have this control signal, very much makes sense from data perspective. Yeah. But I was wondering if you had other benchmark from different communities to compare your solution.
For exactly solving a problem like this, I don't really know about it. But I mean, several other related tasks, they use indeed more control engineering approach. Also, we didn't really start off solving this problem like, okay, we have to use machine learning, right? We kind of looked at, okay, what has been solved already? And then, yeah, came to this approach. But I mean, if there's another problem that we can help a grower with, for which we do not need to use machine learning, so I put like as a recommendation, yeah, then we for sure do that. Also, in the other models that we make, there's quite some components that, I mean, we do not do model training to create. I mean, we might think a lot about a model always being a machine learning model, right? But I mean, that's not doesn't have to be the case. It can be just a theoretical model based on physics that you do not do training for, and it can actually work very well. So yeah, we have some components inside the company, and yeah, there's, I think, a lot of applications. I think for us it's really good too also. We've had yeah, quite some conversations with companies that have more this kind of approach, system engineering.
Yeah, thank you very much.
Yeah, and that also ends our time.